So we define the continuous form of the canonical ensemble partition function in terms of momentum and a position. All right. Of course, it's still in a somewhat uglier form, and so by making additional assumptions, we could simplify it down. Okay. And so one of the common assumptions that is made is that the momentum and positions are independent of one another. Okay? And so if that's true, we could split up the integrals like this. Okay? So we're just going to have integral for the momentum. So we'll write our Hamiltonian in terms of momentum divided by kBt. And here's our momentum vector. And then we have the position. So remember, V is for volume, that's L cubed. We have our potential term. drn. Okay? So we could write these independently of one another. And so because we could write them independently, we could focus on them one at a time. So now let's focus on the momentum integral. So for momentum, if we go back to our particle in a box calculations, we could remember that we could write the momentum contribution like this. 1 over 2m, which is the summation of I pi x squared plus pi y squared plus pi z squared. Okay? Alright, and so if that's true, you could rewrite this integral like this. Okay. Now it's 1 over 2m kBt summation pi x squared plus pi y squared plus pi z squared. And this whole thing is dpn. Okay? I'm now going to split up this vector like this. Negative 1 over 2m kBt. So now we have p1 x squared dp1 x. Right? And then that's multiplied by negative infinity. Show the second term. Negative 2m kBt p1 y squared dp1 y. Then of course we have a lot of integrals, and in the end we're going to have negative infinity to infinity exponential 2m kBt p, the nth particle in the z direction, its momentum squared, dpnz. Okay? Alright, so we've expanded this. We have a lot of integrals, but of course we could condense this again by writing it like this. Negative infinity to infinity exponential negative 1 over 2m KBT, just p squared dp raised to the 3n, which accounts for the number of particles and then the 3 directions. Okay? Alright, now in this exponential we have all these constant terms with respect to the integral. And so what we're going to have is the exponential of negative p squared over some constant a. Right? And as you could recognize, to solve this integral, it's known as a Gaussian integral. So to solve it, just use the same strategy that you've seen previously for solving Gaussian integrals. And what you get is that this will equal this, 2 pi m kbt raised to the 1/2 3n. Okay? Or we could bring this out here. What we get is 2 pi m kbt 3n divided by 2. Okay? Alright, so kind of backtracking, we find that the momentum portion of the partition function just simplifies down to this constant expression. And so if we go back to the continuous form of the partition function, what we have is this. I'm going to leave the factorial by itself. But here, I'm going to write this, m kbt divided by, now I brought in the Planck's constant, have the 1/2 here, and then I'm going to write it as 3n. And then we have 0v exponential negative v r to the n kbt drn. This you may recognize as the inverse of the thermal wavelength, so that capital lambda. And then here, with our position term, essentially we're accounting for the potential energy interactions, there are the potential interactions between the different molecules. Okay. Here, so this is where, depending on the interactions that occur between the molecules, this is what will change the overall partition function. And so a lot of times, we will refer to this portion of the partition function as the configurational partition function. Okay? And so, in the end, our continuous form of the canonical partition function we could write like this. Z, which is going to be a function of t, v, and n, over the thermal wavelength raised to the 3n divided by n factorial. Okay? And so this is the continuous canonical partition function.